So next, I'm going to walk you through the file system, a list of file system interfaces, specifically Unix file system interfaces, okay? Or Linux file system interfaces. So the very first set of file system interfaces are creating files. So under a Unix-like operating system, how to create a file is by calling this basic system call API, which is called open. Okay? So there are these two different forms in terms of this open system call. So the first parameter, it has a 3-parameter version as well as a 2-parameter version. So both of these are used in practice, but often, from my perspective, based on my experience, I tend to use the second form more often, okay, which holds and accepts two parameters. So the very first parameter is a char string-based path name, where you want to open up this file, no matter whether it's a new file that hasn't existed within that particular direction, or it's an existing file that has already been stored there, okay? So how to identify and locate the file is by just passing in the specific string typed path name. So this is the first parameter, okay? So the second parameter, as well as the third parameter, are the corresponding permission configuration parameters that you want to control while opening up the file, okay? For example, the second parameter flag, it specifies the opening mode of this particular file, whether it's read-only or write-only or read-write, okay? So this is the second flag parameter. And the third parameter, the mode, if we're talking about the very first form of this 3-parameter version open system call, so this mode is it's also permission mode, which is a little bit confusing, but it's a permission mode in correspondence with creating a new file, okay? So it's associated with the user access permissions, whether you grant the user, you put the user in the read-only group, write-only group, and so on and so forth. This is the mode associated with a file creation, okay? If you pass in the second flag as the create this new file mode, okay? So the return value of an open system call is a file descriptor, or in short, FD. So this is the third type of, recall that this is the third type of file name abstraction, okay? So it's a runtime state. It's an ephemeral transit state that is only associated with some file that has been opened within the opening mode by a particular running process, okay? So it is an integer, and it's the private per process level resources, okay? So recall that in one of the earlier lectures where we've talked about the process namespace and the process context state information. So the file system context information, or the file related context information that belongs to a particular running process, is this file descriptor, or a set of multiple file descriptors, meaning this running process has opened up multiple files, and each opened up file is associated with a file descriptor, okay? It's a private context state information. Belongs to a certain file. So it's an opaque handle to the particular opened up file that gives a caller, which is the process. As owner, the power to perform a certain file system related operations. For example, read data or write data to the file, close a file, okay, erase a file, and so on and so forth. So how to understand a file descriptor is you can think of an FD as a pointer to an object of the file, okay? An object to the open file. And by owning such an object, by owning such an opaque handle that points to this particular file, you can call the corresponding file system related APIs or methods to access a file or manipulate the file content, the data stored within the file. Okay, so this is the third type of file name abstraction, file descriptor. So let's look back at the open system call. In this slide, it shows one simple examples how to use open system calls to open the same file, okay, or different files. In this particular example, it touches exactly the same file, okay. So the first line, it tries to open this file, which is called file.txt, and it passes in the flag, which is o_create. And over here, create doesn't have the last word E, right? But it's not a typo, it's not a typo. Why is that? It's because, so as a name convention, operating system and the C designer, they specify this name, the name of this particular flag as create without the last letter E, okay? So this is not a typo, so just some interesting thing to know about. Okay, so the result of this open system call is to create the file if this file.txt file doesn't exist, okay? And as a result, it returns a file descriptor, which is an integer 3, okay? Which is basically FD1. And the second system call is you want to read something out from this opened up file descriptor. So we'll be talking about the read system call API in the next couple of slides, okay? So the third line, it shows another call to the open system call. So in this line, it opens up the same file, but with a different opening mode, which is write and read only, okay? So this is different mode, meaning it could be written, it could be read from the disk. As a result, it returns a different file descriptor, which is FD2 with an associate value of 4, integer value 4. So this is the third line. And the fourth line corresponding with the last system call, which is dupe. A dupe pass in the parameter, which is FD2 just returned from the last system call open. Okay, so what it means is this duplicate system call just tries to duplicate the previous, the parameter specified as the file descriptor specified as a parameter, and duplicate and create a duplicate of the same file descriptor. As a result, it has a corresponding file descriptor value of 5. Okay, so in the next couple of slides, I will show you how the underlying, data structure looks like in correspondence to these 4 different lines. Okay, so the bottom half of the slide shows, the left-hand side shows the file descriptor array, which is called the file descriptor table. Okay, it uses the file descriptor value as an index, and in the middle, it shows the file descriptor data structure, which contains some bookkeeping information. For example, the offset, where exactly the offset is within this file. Okay, so starting off, the initial state always have an offset of 0, but this offset value is definitely configurable. Okay, and the second field in this example, it shows this inode number. So this inode number has some specific value, for example, 25 or some random value that I just make up. And this value is essentially a pointer that points to the associated inode data structure shown on the right-hand side of the slide, okay? So this inode number. So this inode number, and we'll have a detailed discussion in the second half of today's lecture when we talk about the file system implementation. But here, just to clarify this inode, it contains the corresponding metadata information that belongs to associate with that particular file, which is file.txt, okay? This file. For example, its location, where exactly located within the hard disk drive or SSDs, and how many bytes it include, and when exactly it gets created, and so on and so forth. This kind of metadata statistics, okay? So the first call to the open system call, it returns a file descriptor of 3. So as a result, to animate, so as part of this animation starting off, you create a new entry under index number 3 of the file descriptor table, and you establish a connection from the file descriptor table to the corresponding file descriptor data structure that you just construct at runtime. And this owner process, the caller process, keep track of this FD table to kind of keep track of the opened up file system related resources, okay? And the second system call is read. And instead, so it just read the first 8 bytes into the second parameter, which is this buffer parameter, pass into this read system call. It reads 8 bytes. So as a result, you update this offset value from 0 to 8 and represent right now the offset cursor has been moved by 8 bytes, okay? And the third line is another call to the open system call. In this case, you open up the same file, but with a different flag opening mode. And instead, it returns a different file descriptor, which is under the index number 4. So you populate the fifth entry under the file descriptor table and establish a connection, construct the file descriptor data structure, and have the file descriptor table points the fifth entry as a pointer, points out to this just newly constructed file descriptor data structure. And you further establish the connection between the file descriptor, which is completely the runtime state, that points to the static information, which is associated with the file that you just opened up, which is the inode of that file, okay? This is the inode of file.txt, okay? So the fourth line, it calls the dupe, okay, which is to duplicate the same file descriptor, fd2, and returns a duplicate of it, which is fd3. In fd3, it has its corresponding index, which is 5, which is associated with the 6, which is the last, in this case, the last entry of this file descriptor table. Because it's simply a duplicate, so it doesn't try to construct a new file descriptor data structure, but instead, it just simply points to this already established, already created existing file descriptor, which is called the fd2, okay? So this is essentially fd2. And right now, a duplicate of itself, fd3, also points to the file descriptor of that belongs to fd2, okay? Because it's simply a duplicate, it is mapped to the same inode. So all of these 2 different file descriptors, all of these 3, they map to the same inode number because it basically touches the same file, which is file.txt, okay? So that completes the open system call. So next, let's move on to the rest of the 3 important file system related APIs, read, write, and close. So in order to read data from an opened up file, a file that has been opened, you need to call the read system call. And correspondingly to write data into it, call write system call. always remember, as a best practice, always remember to close and open the file whenever you're done with processing the file. Okay, so this is the last API, which is close system call. So let's first take a look at the reading and writing. So if you take a look at the read and write, both of them, they take in 3 parameters. So the first parameter are the corresponding the target file to read data from or to the write new data to. Okay, so these are the file descriptors returned by the open system call. Okay, so the second parameter are an opaque, like void type buffer, which contains the data, which contains which is the buffer that would be holding the data to be read from the data or contains the data to be read into the file. Okay, so the third parameter is a size underscore t, which specify how many bytes of data that you want to read from the disk, from the file, or how many bytes of data that you want to write to the open file, specified by the first parameter, which is the FD. Okay. So let's take a look at an example. So in this example, assume we are working with a prompt, a shell, or a terminal. Okay, so where you type echo command line 2, which is simply to display the content of the file name that you pass to this echo 2. In this case, the file name is called hello. Okay, and then you pass in this symbol, which is greater than. Okay, so this symbol simply means you want to redirect the standard output to another file, which is called file.txt. Okay, and then you type return. The prompt further asks you to type another command, right? In this case, you type cat, which is just to simply display the content stored within this file. Okay, so as a result, it just simply display the data that you just echoed in, which is the hello string. Okay. All right, so in this slide, it shows what exactly happening under the hood, under the scene. So how to zoom in and see the corresponding system call related behaviors that are corresponding with a particular command line activity is by using this tool, which is called S-trace. And I introduced S-trace in one of our earliest lectures. So this S-trace is basically a short of system call tracer, which is used to trace underlying system calls associated with a particular activity. Okay, and this activity in this case is this cat file.txt, which is to display the file, the data stored under file.txt, which is a plain text file, which stores a string of hello. Okay, so under the hood, it involves the following system calls. So the first one, it tries to open up the file, because in order to display the content of it, you need to first open it up. Okay, so the first parameter is the string to the file name, and followed by the opening flag, the permission flag, which is read only. Okay, so this is read only. And as a result, it returns the file descriptor, which has a value of 3. Okay, so FD has a value of 3. So this is the first system call API involved. And moving on to the second system call, which is a read. As expected, because you want to display the content. So first, you need to read something, read the whole content out. In this case, you try to, so the target file has a file descriptor of 3. So you just pass in a return value from the previous open system call as the first parameter to this read API. Okay. And the second parameter, this part, instead of hello, you can understand it as some sort of, opaque buffer. So this is essentially a buffer. And the third is the maximum data that you try to read into the buffer. In this case, it's a 65,536, but in this case, this file is so small that it only contains like 6 characters, 6 bytes, okay? So as a result, you just return the total number of bytes that you read from the file, which is 6. And moving on to the next call, which is a write. So why we have a write system call is because we want to display, right? Because this is a cat. It tries to display the content to the terminal, to the standard output. Okay, so the corresponding file descriptor associated with standard output is some reserved file descriptor, which is 1 in this case. So that is why you pass in the first parameter as an integer 1. Okay, so just try to write the string that you just read from this file to the standard output fd1. Okay, you write exactly 6 bytes because it just hello followed by the new line symbol, which is 6 bytes. So just simply return total number of bytes you've written to standard output. And then followed by the last, the second to the last system call API, which is read, because the cat tries to read more, but it eventually hit on a end of file character. So you basically stop reading. This is end of file, EUF. End of file character. So it just basically terminates the read activities. There's no more to be read from. So followed by the last system call, which is close, which is part of the best practice, right? Whenever you're done with processing, with reading, writing of the opened up file, always remember to close it. And to close which file? To close the file that you've opened associated with the file descriptor has a value of 3, okay? So just close on file descriptor number 3 to close the file, okay? So this is the system call level activities involved under the hood by just typing cat to display a file named file.txt. Okay. So in order to support non-sequential or random small read and write, random small file operations, you can call lseek. Okay, so this is try to just locate and put the file offset cursor opened up file to a specific position specified by the parameters of the system call. Okay, so the whence is the flag that you can configure. So if the whence is set to seek underscore set, then the offset will be set to the offset bytes specified by the second parameter. Okay, if otherwise the whence is set to seek underscore cur, the offset will be set to its current location plus the offset bytes. So note here there are some subtle differences. Okay, and the third case is if the whence is set to seek underscore and, then the cursor, the offset cursor, will be set to the end of the file, to the size of the file, plus offset. Okay, plus offset, meaning you want to append something, but still with a stride of offset bytes, something like that. Okay, so just to remember this, you can always use lseek to basically move your cursor back and forth in a configurable manner. So the caveat of lseek is calling lseek doesn't necessarily result in some disk operation, disk-specific operations that has something to do with the moving parts of the mechanical hard disk drive. It doesn't necessarily perform a disk seek, but simply manipulate this in-memory state, for example, that offset field, which is some in-memory state. So it has nothing to do with the underlying hard disk drive activities, mechanical moving parts, okay? So the next API is fsync. So if you want to write immediately to the hard disk drive, you can call fsync, and with a one and only one parameter, which is the file descriptor, okay? Because in order to write something, the operating system always buffers a write within the memory in order to accelerate the performance, to improve the performance of the write operations. And whenever the in-memory buffer is full, operating system triggers a flush operation to the disk. But you can also, as a user, you can also manually call fsync to manually enforce this data flush from the memory to the disk. Okay. So in the next couple of slides, I'm going to walk you through some other important file system related APIs. So in this slide, we're looking at this how to rename a file. So to rename a file from a command line from a terminal or a shell, you just need to call this command line 2, which is called mv, to basically move a file from its old name to a new name. In this case, you want to change the file name from file.txt to new_name.txt. So let's again use strace to see what exactly happened under the hood in terms of system call level activities. So essentially, this mv, this move command line 2 is associated the core API, core system API, which is called rename. Okay, so this rename system call just simply rename a file from its previous name to the new name. Okay, and once successfully executed, it returns a return value of 0. Okay, so this is how to rename a file. And in real world, in practices, there are lots of examples that involve rename operations. So if you have experience working with this Vim text file editor, so whenever you open up a file using Vim, the Vim program creates a new temporary file, which is dot followed by your file name, followed by its specific extension name, .swp, okay? So this swp represent swappable swap file, okay? Which is a temporary file. Managed by Vim. Okay, you just create a file, and for whatever read and write, it all targets this temporary file. You use this temporary file as some sort of, write buffer. And then, let's say this user go ahead starts the editing session, Vim editing session. It types like random characters and store those random characters within a memory buffer before the memory buffer gets fully flushed to the on-disk file. So this involves multi-call to this write system call. Its first parameter is fd, returned by the previous invocation to the open system call. And the second parameter is some in-memory buffer that holds the data that the user typed in, okay? And the third parameter is the size of the buffer, how many bytes of data that you want to write into the buffer. And then at a certain point of time, this user hit WQ in order to save and quit this Vim editing session. So this WQ kind of command triggers the following set of system call APIs. Specifically, the first one is fsync. Okay, recall that fsync means to reliably and to make the data, to make the in-memory buffer data durable by flushing all the in-memory buffer data into the disk, into the corresponding location of the disk that belongs to this particular file, which is file.txt, which is a targeted file of this Vim session, okay, to make data durable. And then WQ means you want to save and close it. Q means quit, right? We just close this file by calling close system call. And as a final, last important critical step, which is involving this rename API, okay? So this is a key part. So the last step is to change the name of this temporary file, which is file.txt.swp, to its original name, which is file.txt, okay? You need to change the name and basically replace the old file. The old file, which is the file.txt, but with a previous relatively stale version, okay? You wanna rename this temporary file to overwrite this existing old file. So this is what exactly happened if a Linux user wanna use Vim to open up a file and perform some editing and save it and quit it. So the next operation is to delete a file. So assume we are working with the terminal again. How to delete a file is by calling remove or rm command line 2. Okay, this rm. And in order to remove a directory, you need to call rm with the specific runtime flag, right? F. Okay, because you need to forcibly delete the whole directory. Otherwise, you cannot delete the directory, right? Okay, so the underlying system call involved by calling rm if you run the S trace is unlink. Unlink means you want to cut the connection between the file system with this particular file. In this case, you call unlink to this file, and once it's successfully executed, it returns a return value which is 0. Okay, so the system call unlink is used to delete a file. How to understand it? You can understand it as a way that it tried to disconnect the relationship between this file and the file system as a manager. Okay, so directories can be deleted when unlink is called as well, right? So the question over here is, when are the file descriptors or FDs deleted? Okay, so because file descriptors are some runtime state, whenever a process as a caller opens up a file, it creates a corresponding file descriptor. So the file descriptor gets destroyed or gets deleted when the file gets closed, okay? Or when the process quits. The owner of the file quits. Okay, so there's two different kinds of scenarios because it's just some runtime ephemeral state. It doesn't persist. It doesn't make the operating system doesn't try to make it durable as some external on disk state. Okay,